University of Auckland, and Lorna is a sedimentologist.
A sedimentologist is someone who studies sediments, whether they're grains of sand or if they're sedimentary rocks. And what we're always trying to do is work out how those sediments got there. So the processes involved, so whether they moved in a river, for example, and then what that tells us about past environments. So they're really important archives of Earth's history.
What are you going to be drawing for us today?
Okay, so today I want to talk to you about something that not many people know about. So you know about rivers on land, but actually we have this amazing network of things that look like rivers on the ocean floor. So obviously in the deep ocean we can't get there to measure it. So the deepest divers on the planet Earth can only go to about 100 meters, and the world's oceans go to about 12 kilometers. If we imagine the land and we move to our coast and we have our ocean here, and we'll put a little fish in for scale. If we look at the ocean floor, it's really rough, like the land. So we'll have lumps and bumps, mountains, and we have steep slopes that go off into the deepest part of the ocean. And what happens if we have, for example, an earthquake, so let's say a little fault at depth, is we start to shake that surface. And what happens is we can generate a landslide, which starts to fall down that ocean floor, and as it moves off, it turns into something else. So it starts to accelerate, and it turns into a flow that we scientists call turbidity currents, which is a bit of a tongue twister. And turbidity currents, if you were to take a cross-sectional look through them, look a little bit something like this. And this rather confusing name basically just means a turbulent cloud of sediment that moves through the water column. And it's very turbulent and they're very big. So these things can be several hundreds of meters high and many kilometers long, and they're really destructive. If you were a little fish down here and this was coming towards you, it would look something like a pyroclastic flow or a desert sandstorm approaching. So it's basically this big boiling cloud of sediment and gravel and dead bits of fish and shell all coming at you at tremendous speed, and as they go they're ingesting the seafloor as they move. And we know about these because in 1929 in Newfoundland there was an earthquake, and what happened was that triggered one of these landslides that then turned into a turbidity current. And in 1929, there were a whole series of seafloor cables that joined North America to Europe. This was literally the only form of communication transatlantic via these thick cables, and they sent Morse code and telegrams and everything through it. And what happened was, one by one, each of these cables snapped as this turbidity current moved through them. So then scientists kind of had a record of something highly destructive moving across the Atlantic. And it was only in 1929 that scientists started to think about this idea. And it wasn't really until the 1960s that the idea took hold. In New Zealand, we have one of the world's biggest underwater rivers. This is the North Island, and we'll just do the top of the South Island here. And lots of you will know the Kaikoura Canyon, great place to go and do some whale watching. And the head of the Kaikoura Canyon, if you like, is the headwaters to this huge underwater river, which flows all the way from the South Island, all the way up past the east coast of the North Island, takes a slight detour, and then it eventually ends in the subduction zone up here. And this is known as the Hikurangi Channel.
So can you give us an idea, how big is the Hikurangi Channel?
It's big. So it is about 2,000 kilometers long, And at its widest, somewhere in here, it's about 10 kilometres wide. So to put that into perspective, the mighty Waikato River of New Zealand is only about 450 or so kilometres long. So it's 4 times as long as that, and it's much, much wider. So you can imagine if you were in the Hikurangi Channel, a little critter on there, the flows that must come down there are gargantuan, and they go for thousands of kilometres. And much like rivers, they bend and they move and they have lots of complicated things that happen with them. And in November 2016, obviously we know that there was the big earthquake in Kaikoura. And what happened was that the fault systems that ruptured, which were quite complicated, also ruptured some faults offshore. And what this meant was that all the sediment in the head of the Kaikoura Canyon collapsed. So much like the Grand Banks event. So this all collapsed and shed all of its sediment into the Hikurangi Channel. And we know from going out fortuitously on the Tangaroa Niwa's ship at the time that we had sediment being deposited by a turbidity current for at least 600 kilometres. And we just simply haven't been out here. So it could have gone the whole way, all the way to the trench. So Niwa and a whole bunch of scientists, including some of the students that I work with, happened to be out on the water when the earthquake happened. And so what happened was they diverted the ship and they took a whole bunch of samples all the way down part of the channel 3 days after the earthquake happened. So this is the most fresh sampling of an earthquake triggered turbidity current that has ever happened. So this is one of those things in science where, although it was really unlucky the earthquake happened, we just happened to fortuitously be out on a ship. So we're starting to learn quite a lot about what happened now.
So why are we actually interested in studying these turbidity currents, these flows under the water?
Okay, so we're interested in them for a number of reasons. So one, they're a really important archive for ancient climate and ancient earthquakes. And two, they're really important because they tell us of where all the sediment from the land is going in the ocean. So they form this amazing archive of Earth history.
Yeah, and that's what a geologist does, isn't it?
Yeah.
Well, that was fantastic. Thank you so much for coming and talking to us on Science on a Napkin.
Thanks.